Okay then. So welcome back to week 5 of the problem solving session for the Introduction to Fluid Mechanics course. And uh, and this week we will be dealing with some core concepts regarding fluid visualization and fluid kinematics. So let's wait for a few minutes for the other students to join, and then we can start. I hope that's okay. So let's wait for a few minutes for the students to join, and then we can start. Okay. Again, so because of the content of this week's session, today's session won't be that long. It's highly conceptual based and few simple calculations, so I don't think it will take much time. So I hope that we are able to cover up the agenda that is planned for today within a short period of time, and then directly look into the problems and then complete the session. So I hope that's okay with the students. So okay, yeah, I hope that's fine. Just let's just wait for few more minutes and then we can start. Okay. Okay then. So I believe we can start the session, and the students can obviously join the session accordingly. Uh, that's fine, but let's move ahead to this session. And okay, so as I already mentioned, this week's session, and as per if you have attended Professor Chakraborty's lectures, you would definitely know that. So this week's session would be primarily be the introduction to the fluid kinematics and a very brief overview over fluid flow visualization. And as you can see that the fluid visualization techniques I don't think will be discussed thoroughly in this course, but still the primary concepts regarding fluid visualization, that is primarily the streamlines, streak lines and path lines, will be discussed in today's session, and how they are different, and under what circumstances they are same, that will be revisited. Then we will look into the concepts, the two concepts of fluid flow analysis, or two approaches of fluid flow analysis, that is the Lagrangian and the Eulerian approach. And nevertheless, we have discussed about both of them in the first session, in the introductory session, but still we try to revisit and try to understand, at least have a brief overview of what these two approaches are and how they are different. And I'm definitely sure that Professor Chakraborty might have definitely discussed it very thoroughly and in detail about these two approaches of fluid flow analysis, and under what circumstances, how they are similar and how they are different. So Professor Chakraborty had discussed it thoroughly in his session, so I don't think I need to repeat it uh, for the sake of saving time for today's session. So I won't be repeating it each and every bit of it, but we will revisit it briefly. Okay, and then we will look upon the concept of acceleration in fluid flow, and primarily dealing with the uh, Eulerian perception of acceleration in fluid mechanics. Then we will deal about deformation of fluid elements, and finally we will end up by discussing the continuity equation, or how the derivation of continuity equation is done. Okay, but as I already said in all the sessions before this session, that this is not a lecture session, it's just a problem solving session. But I believe that before solving the problems, it's a good practice to look back and revisit the concept, so that it gets freshened up, and so that you can uh, tackle the questions that we will be discussing in today's session with more rigor and a better understanding. Okay, so keeping that in mind, let's just directly dive deep into the topics that we have planned for today's session, starting with the Lagrangian approach. So as discussed with Professor Chakraborty, Lagrangian approach is an approach of studying fluid mechanics where the entire analysis is done by following each and every particle in the flow domain. Okay, so a Lagrangian approach involves following a particular particle, say this one, then uh, evaluating its flow parameters at each and every time step, at each and every time instead of time, and each and every instant of time, and understanding how the parameter changes because of the evolution of this particle through a domain with respect to time. Okay, so that's basically Lagrangian approach, and uh, of course Lagrangian approach gives highly accurate results and can be very useful for the fundamental understanding of the flow physics in different kinds of flows, and it's also used in understanding the, for example, it's also extensively used in understanding the behavior of particles in different kind of flow regimes, varying from uh, highly viscous flow or the Stokesian regime to highly turbulent flows. So to understand the behavior of the particles that are suspended in such kind of flows, Lagrangian approaches are highly used to track the particles and the behavior in the flow field. Okay, but as it logically comes into picture that these kind of approaches would be highly expensive computationally, and is thus uh, not being replaced but aided by a different kind of fluid flow approach that is known as the Eulerian approach, where the flow parameters where the flow parameters of the fluid flow is analyzed with respect to a particular fixed point at a given instant of time. Okay, so consider that there is a fluid consider that this is a fixed point with respect to which we want to study the uh, variation of flow parameters in the fluid flow. So this kind of approach is hence termed as the Eulerian approach, and since this Eulerian approach depends the on the temporal as well as the spatial coordinates, which is fixated by the choice of our frame of reference. Thus, the flow parameters in an Eulerian approach is dependent on both the spatial and the temporal coordinates. Okay, so I hope it's clear, and the definitions, or at least a visual explanation of these two different approaches were pretty self-explanatory. But again, if you have any doubt, I will just insist that you go on and look back to the lectures by Professor Chakraborty. He has at least in this week's session, since Professor Chakraborty has extensively discussed about these two approaches with ample amount of examples. So that would be the best way of understanding this these concepts. But still, I hope if you have any doubt, you can just ask me. But I think it's it's quite self-explanatory uh, uh, up till now. Okay, so uh, just 1 minute. Okay, sorry for the delay. Just 1 minute. Okay, I'm sorry for the delay. I hope it was clear. Okay, and uh, nevertheless, let me just give you another visual representation or understanding of the differences between these two approaches. I hope this space will be enough for the drawing that I'm trying to do, but I have explained this example previously as well, but still. Okay, so let's consider a box or a just say a cubical duct through which there is a certain fluid flow. So let's consider this to be the two streams of fluid going in and out of this particular duct. So just forgive my accuracy of the drawing. So that's fine, but I hope it is to make you understand the concepts. Okay. Then these are the two streams of fluid flow. Let it let me name it as the inlet and the outlet. Okay. So as per the Lagrangian approach of understanding or analyzing the fluid flow, this fluid flow can be considered to be composed of n number of particles. Okay, n number of fluid particles. And the definition of fluid particle, I don't think I need to revisit again, but I insist that you go back and revisit the definition of fluid particle. But still, so these fluid particles, there will be n number of fluid particles in this particular stream of flow, right? And these n number of particles will then interact with this duct. Okay, this duct through which the flow is passing through, and this duct may be of any shape. It may be a converging diverging nozzle, right? It can be a nozzle, or it can be a diffuser as well. Okay, and depending on this shape also, the flow parameters will change, essentially the pressure and the uh, velocity. It might also happen that the duct is being heated from its periphery or from its boundaries, which may also affect the fluid flow, right? So nevertheless, according to the Lagrangian approach of the fluid flow, it is the these individual particles that interact with this duct and hence create changes in the flow parameters accordingly. Okay, then what would happen is that in the case of Lagrangian approach, when these individual particles are then are actually tracked throughout its movement through this duct. Okay, say there is a single particle, say there is a particle 1, right? P1, say P1, and this particle uh, would then move around this duct according to the velocity field that is being generated, right? And it may also interact with the surface of the duct, right? Then bounce back here, then hover around somewhere, and then move out of this uh, duct. Okay, assume that the flow has become turbulent for some, or the inlet flow itself was turbulent, that has resulted in the formation of eddies, that has resulted the in this part in the part resulted in the particles of the fluid to move around, hover around in this duct, interact with the surfaces of the duct, and then move out as a turbulent flow again from the outlet. Okay, so this interaction of the fluid uh, is understood or analyzed from on the each on the particle level. Okay, so this interaction is then studied on particle level, and the corresponding change because of these interactions is then finally summed up, if possible, to find the net effect of, or the net effect of these interactions on the variation of the flow parameters. Okay, so this is how the Lagrangian approach is followed. But in the case of oil, and obviously you can see, like, it's just the trajectory of one particle. So say, even if we are going to and if we are going to model numerically, so a single particle would require a proper modeling of the trajectory of these particles throughout the flow. Okay, and if the flow is turbulent, that itself causes a more highly expensive computational setup, right? Then again, we need to model these interactions with the walls as well, right? The uh, collision with the wall and the resulting deflection in the trajectory of the particle. All these things have to be modeled. Then it may also happen that these free particle may interact with each other, right? That's obviously possible. So this modeling has to be done for the accurate analysis of the fluid flow, and thus measure the corresponding change in the flow parameters, which is essentially the pressure and the velocity. Okay, if at all there is no heating involved. Okay, so I hope now you understand why this approach is not usually appreciated by the engineers for simple fluid flow analysis. Okay, and that the thing that I was discussing is for a single particle. Now consider there are n number of particles, n would be very very large, and you have to do this analysis for all those n number of particles. So I think it gives you a very proper idea of how much computational expensive it is going to be just to get a understanding or a conclusion of how the flow parameters are changing by the passing of this jet of fluid fluid stream through a simple duct. Okay, so I hope now you understand the depth of calculations, or the expense of calculations, or the cost of calculations or analysis or computations that had to be done just to analyze this simple fluid flow from the Lagrangian approach. Okay, but in the case of an Eulerian approach, this duct is now considered as a black box. Okay, so the we are now not interested in how the fluid will behave within the duct, but rather we are interested in how the flow parameters are behaving at the boundaries of the duct. Okay, or any geometry on which we are trying to understand the interaction of the fluid flow, and how this interaction then changes the corresponding fluid flow parameters. Okay, so that is what we are primarily concerned about. So in the case of an Eulerian approach, we uh, uh, fix our area of focus or area of interest, right? And in this case, that would primarily be this duct. Okay, or this boundary of the duct is interacting with the fluid. Okay, and an interest and for understanding how the flow parameters changes at the outlet because of the flow of the incoming stream through this duct, uh, the only thing that we need to know to do we need to know a priori to get the final results is the initial profile of the fluid flow that is approaching the duct. So that is a simple parabolic profile. It's just an assumption, okay? It can be anything, but I'm just saying for now I know that the incoming stream is in parabolic velocity profile, and thus if we know that, uh, we can apply mass conservation to know how the velocity is going to change, or velocity is going to change at the outlet, right, by applying mass conservation, and then finally use the momentum conservation to in fact get the pressure also. Okay, so this is the concept that is being used in the case of Eulerian approach. Okay, and by no means I'm going to say that Eulerian approach is much more accurate than the Lagrangian approach, because Eulerian approach also comes with the different uh, what to say drawbacks, as there are lots of assumptions involved in the Eulerian approach, right? The assumption of a parabolic velocity profile, or no losses. There are certain kind of there are many approximations that we need to consider before applying the Eulerian approach, right? But these kind of assumptions need not to be done in the case of Lagrangian approach, right? We can just directly follow the particle of each and every particle of the flow, and then find the corresponding change of flow parameters. But for the Eulerian approach, it's a very standardized or idealized scenario where we are assuming that these kind of idealistic assumptions are correct, and thus the analysis would give us a expected expectably or acceptable accurate result. Okay, so every analysis comes with their own pros and cons, but as an engineer it's our duty to understand which is more effective, or which is more efficient rather than accurate, right? So it turns out that Eulerian approach turns out to be much more efficient in our day-to-day engineering applications, and thus has been selected by the engineers as a preferable choice of fluid flow analysis for most of the engineering fluid flow problems. Okay, and that is what we are going to primarily discuss in the rest of our course, how the governing equations from the Lagrangian point of view are converted to the for the Eulerian approach using a certain theorem known as the Reynolds transport theorem, which we'll eventually discuss in the following classes, and how to apply the the Reynolds transport theorem effectively by choosing a proper control volume, a suitable control volume for our fluid flow analysis. All these things would be discussed, but I hope this discussion that we had right now gave you a proper understanding or a proper overview of what we are going to deal with in the rest of our course. Okay, and why an Eulerian approach is considered to be much more suitable for a mechanical engineer rather than the Lagrangian approach. And by all means, I'm not saying the Lagrangian approach is useless or not at all worthy to be discussed about. It's a topic of discussion for many researchers, and it's a topic to be and it is a topic which has high research scopes, especially in the regime of turbulent flows. But still, just for an introductory course or an introductory lesson for an aspiring engineer, an Eulerian approach for understanding fluid flow analysis would give a much more deeper insight to the physics of the flow rather than an advanced and highly computationally expensive topic such as the Lagrangian approach. Okay, and that's why this is preferred here for this introductory course. But still, I hope now both of these approaches or concepts are quite clear to all of you. Okay, so I hope that was insightful for all the students, and I hope I was able to clear the doubts of the students. But let's now move ahead. Okay, so okay, so following the discussion with following the discussion of these two approaches, there is the Eulerian and the Lagrangian approach. We now discuss about the different flow visualization techniques that has been what to say that has been conceptualized by the researchers to understand this, to understand the behavior of the fluid flow undergoing different subjected to different kind of uh, flow regimes. Okay, with that I am primarily talking about the Stockton regime or the turbulent regime. Okay, so the Stockton regime would primarily correspond to a highly viscous fluid flow regime, where the Reynolds number is uh, primarily close to is primarily very, very less than 1, and in the case of turbulent flow, the Reynolds number is much greater than 1. Okay, and as by the terms itself, I feel you know that a Stockton regime would correspond to a fluid flow which is highly laminar. By laminar, I mean that it would have fluid flows flowing in different layers with high uniformity, with no distortion in the velocity profile or the streamlines, and is can be considered to be highly idealized way of uh, visualizing fluid flow over objects. Okay, but the turbulent regime also comes with their own benefits, as most of the flows that we encounter in our day-to-day life is turbulent, and as as the name suggests, or by some prior knowledge, if you know the a turbulent flow would for a layman would correspond to a highly irrotational flow with uh, vertical structures varying from different vertical structures varying in different sizes, and these vertical structures are also termed as eddies in the case of turbulent flow, which would have high level of distortion in the streamlines uh, in the case of turbulent flow, but still uh, and to visualize this kind of flows, the concept of visualize these two extreme regimes of fluid flow, this the Stockton regime and the turbulent regime, and how this fluid flow or fluid flow or fluid particles behave in this kind of flow regimes, the concept of fluid visualization came into picture. With that came the concepts of streamlines, streak lines, and path lines. Primarily these three. There can be many other flow visualization techniques, but from an analytical point of view, these three were considered to be the cornerstones of flow visualization. Okay, so the first one is a streamline, and again, uh, I would for the sake of uh, saving time, I would not dive deep into each and every definition, example, and such things for this current problem solving session. So let's just go to the basic definition, the governing equations if at all there is, and then a simple example, and then we'll directly dive to solving some problems. Okay, so I will not go and explain each and every line and definition of the these three different kind of flow visualization techniques, but I insist that these are very important fundamental topics that you need to understand. So I will insist that you go and revisit the lectures again. If needed, follow the book by Professor Chakraborty himself, the Introduction to Fluid Mechanics and Fluid Machines by Professor S.K. Som, Professor Gautam Viswas, and Professor Suman Chakraborty. Then you will get a very good insight to this kind of uh, concepts. Okay, so okay then, by streamline here, uh, these streamlines are then defined as the imaginary lines in the flow field such that the tangent to these lines at any point of time represent the instantaneous velocity of the fluid flow at that particular point. Okay, so I won't go to the derivations. So finally, I will just discuss the equation of the streamlines for which is given by this equation. Okay, the detail of the derivation is given in the lectures. I will suggest that you go to the lectures and revisit and understand the detailed derivation. But for today's session, only this formula would be enough to derive the equations for the streamline. Okay. Then we go to streak lines, where streak lines are defined as the locus of all the fluid particles which at some prior instant of time pass through a common point. Okay, so for example, this is the point P. Say P is the point that we are focusing right now. So so a streak line would be the locus of uh, so a streak line will be locus of all the particles that has passed through this point P. Okay, so let me try to make you understand that. Say for example, this is the point we are focusing in, and coincidentally it may happen that this is the point of injection of our dye or any coloring agent that we are used to visualize the streak lines. Okay, so what will happen is that once we inject the dye here, say a blue colored dye in this case, particle 1 will be injected here and move to this position, say after some instant of time. Okay, let me actually number it in a different manner so that I can make you understand. Okay, so sorry for the confusion. So let me just try name it, say 1 2 3 4. Okay, I hope it's clear now. Okay, so let's assume that the particle 1 was injected at this point at say time t1. Okay, at an instant of time t1. Then after this and this is the our point of interest. Okay, point P, or the point of injection in this case. Okay, so particle 1 has been injected at point P1 and has traversed a distance, say uh, u u delta t. So it is u delta t and has reached here. Okay, so this is now the this is now the particle 1. Okay, similarly, say at time t2, particle 2 was injected here and has reached after some time, has reached at this position. Okay, similarly at instant t3 the particle was injected here and has now the particle has reached at this point, and finally at say instant t4 the particle was injected at this point P and has now traveled to a distance, say u delta t4. Okay, just an example. Okay, don't go back to the mathematics of this, but just a vague trying to give a vague understanding of this scenario. Okay, so the commonality between all these particles is that all these particles have passed through point P. Okay, at any instant of time. Okay, at least for some instant of time they were in the point P1 and has now traveled certain distances. Okay, and it is not necessary that they should be all aligned to the same line. Okay, it may also happen that the particle 1 may be now here and particle 2 may be here, particle 3 may be here, and particle 4 may be here. So at that point, so let me just give an example. So particle 1 may be here, 2 may be here, 3 may be here, and 4 may be here. Okay, and if that's the scenario, then the streak line or our streak line would be of this manner. Okay, so the only thing that is common between all these particles is that they have passed through the same point at any instant of time. Okay, at any respective instant of time they have passed through the same point P. Okay, and streak lines would be the locus of all these particles that have passed through point P at a particular at any instant of time. Okay, so we want to find the locus of all these particles that has passed through point P. Okay, and this may be a bit difficult to perceive at initially, and I hope that I'm trying to say it as the in the most simplest way possible. But still I will insist that you go back and see the definition, try to understand it sorry, a bit more, and then try to understand the importance of the concept of streak line. Why? Because most of the flow visualization techniques that are used to see the flow patterns, say in the case of pipes or or channels, for example, by using dyes, we use the coloring agent to color the trajectories of the particles in the fluid flow and then visualize them as the corresponding streak lines, streamlines, and path lines. But actually, by the proper definition that is being given here, the lines that we see after the injection of diet to a particular kind of fluid flow, those lines are actually the streak lines and not the stream lines. Okay, stream lines are imaginary lines that are not actually that cannot be actually visualized, but streak lines are the lines that are actually being visualized in the case of all the flow visualization techniques that are being used. Okay, and that's why they're very important. Physically, they're the most important lines to be understood uh, fundamentally to understand these flow visualization techniques. Okay, and finally, path line. And path line is the simplest one of them all. The path line is basically the Lagrangian description of the fluid flow. Okay, so how? Say, we know that from a Lagrangian point of view, all the flow parameters would be a function of time and their initial position. Okay, so let us assume that, so for a particular fluid particle, say the x velocity would be given by, let me use a different color, would be given by u is equal to dx by dt. Okay, simple definition, simple uh, derivative. Okay, simple definition. Okay, now to find the path line or the trajectory of the particle or the x coordinate of the particle at different instances of time, we integrate this expression, right? So x would be, uh, let me write it as, it's important. Okay, so dx would be integral u dt from the initial time t naught to any time say t, then from initial position x naught to that corresponding coordinate would be which would be at say time t equal to t. Okay, so this would then give us x is equal to x naught plus u t minus t naught, and this would be the equation of the x coordinate for the particular fluid particle, and thus correspond to the path line of the fluid particle. Okay, so this is the definition of path line, and thus they describe the Lagrangian approach of understanding the behavior of fluid particles. Okay, so I hope it's clear now. Now let's understand a very important concept. Okay, a very important statement as per se. So it's a very important statement and may come in one line as a 1 mark question in many competitive exams such as GATE, ESE. So the definition is that for a steady flow, streamlines, streak lines, and path lines are identical. Okay, it's a very simple definition, one line definition, and whose explanation is being given here, which I'm not going to repeat. I will leave you as an exercise for you to understand how they are similar. But it's a very important statement, and thus can be used to approximate using as a sorry used as an approximation to visualize streamlines in the case of steady flows or almost steady flows. Like for example, if you are visualizing very highly viscous fluid flows by using say a coloring agent or a dye, then what we actually visualize or see are the streak lines. But if we say that the flow can be considered to be essentially a steady flow, in that case those streak lines will be identical to the uh, streamlines as well as the path lines, and thus we can say that the lines that we are visualizing are essentially the streamlines of the fluid flow as well, right? But fundamentally streamlines can never be visualized, at least physically, right? What can be visualized is only the streak lines. But in the case of steady flows, we can say that since these three lines are identical, we can say that the lines that we are seeing or visualizing are essentially the streamlines of the flow as well. Okay, so that's a very important definition. And okay, so let us deal with an example, and before that I will just ask you to give me 2 minutes. I will just be back. Okay, and in between that, I guess you can just revisit the concept that we have discussed till now, the governing equations that we have discussed, and that would be okay. Okay, just few minutes. Okay. uh, I'm extremely sorry for the delay. So I hope I was not too late. So okay. So after discussing the basic definitions of streamlines, streak lines, and path lines, and also looking into their governing equations, let us just try to solve one problem. Okay, and this problem was discussed by Professor Chakraborty in the video lectures. So it's fine that if you are able to recollect, you can help me out to go through the different steps of the problem. But and if you have any doubt, again, if I'm not able to clear it properly in this session, you can just revisit the lecture by Professor Chakraborty. Okay, so just read the question here. So the question is, given the velocity field u, v, and w, that is the different components of the velocity field are given, find the equation of streamlines and streak line at t equal to t1 and the equation of path line. Okay, so since it is a 2D velocity field, since the z component of velocity is 0, the equation of streamline is given by this equation, right? Dx by u is equal to dy by v. So we just substitute the value of u and v in this equation to get that dx by ax plus 1 1 plus 2t, sorry, dx by ax into 1 plus 2t is equal to dy by by. Okay, then then we just, and since equation of a streamline is found for a particular instant of time, okay, because it gives the streamlines gives the instantaneous velocity or the instantaneous velocity of the fluid particle at a particular point. So I'm sorry, streamlines give the instantaneous velocity at that particular point. Okay, so we take the value of t is equal to t1, okay, because it's for a particular instant of time, and thus this t can be taken to be equal to t1, which would be a constant now. And since all these terms are constant, we can now integrate these terms to get that to get the equation of the streamline as 1 by a plus 1 by a into 1 plus 2t1 ln x is equal to 1 by b ln y plus some constant c1. And this constant again can be found out by substituting the value of the initial position at these points, and then we can find the value of c1, right? Because so if we substitute t is equal to 0 here, t is 0 here, it will correspond to, it will just be, the equation would just take the form 1 by a ln x naught is equal to 1 by b ln y naught plus c1, because t is equal to 0, initial position is x naught y naught. From this you can find value of c1, which I'm not going to do. Then substitute the value of c1 here to find an equation for x and y, which is dependent on x naught and y naught only. Okay. So in the case of streak lines, we deal with the same equations, the dx by dt, or u is equal to ax plus 1 ax into 1 plus 2t, and dy by t, or v is equal to by. Okay. Then comes then similarly we need to find the expression for x. Basically we need to find the trajectories of these particles, so it will give us the spatial coordinates, right, x and y. So in order to do that, we need to rearrange these terms and find an equation for x and y. Okay, there lies the trick, or the differentiating factor in the case of streak lines, streamlines, and path lines. Okay, which we are eventually going to see. So we follow similar steps. For example, say for x, we just use separation of variables to write the equation in this form, and then integrate from x naught to x and ti to t. Okay. So the interesting thing is that in this particular equation, ti is the variable. Okay. Why? Because for each and every particle that whose streak line we are going to obtain, ti will be different. The time of injection of this particular particle would be different, right? It will correspond to a different initial time for each and every particle, and thus ti would vary from particle to particle. Okay, and the streak lines will actually be different for every particle, right? And thus we need to consider different ti for each and every particle. A similar case can be considered for the y coordinate. So similarly, we use the separation of variable here as well, where the limits for y would vary from y naught to y, and time will again vary from ti to t. Okay. So once the integration is done, we get that ln x by x naught is equal to a t minus ti plus t minus ti whole square, and ln y by y naught is equal to b t minus ti. And since ti is a variable here, we can try to eliminate ti from the two equations to get the relation between x and y. Okay, that you need to do accordingly to find the equation for streak lines for the given fluid flow. Okay, and finally for the path lines, again it's pretty simple, because we just discussed it few minutes before. So again, same equation, u or dx by dt is equal to ax multiplied by 1 plus 2t, and v or is equal to dy by dt would be equal to by, right? Again, we just use the same concept of separation of variables. We write the equation in this form and do the integration. And again here we need to check the limit of integrations for this defined kind of we need to check the limit of integrations for the in this case for x, it will again vary from x naught to x, and but for t here now instead of being a variable, the lower limit would be same. Okay, it will be the initial time point of injection for the particular particle, right? Because since streak lines are actually the locus of different particles that we plot, but in the case of path lines, it is the trajectory of a single particle, and thus the point of injection of a particle would be, for a single particle, would remain the same throughout the tracing of the particle, right? So t naught would remain a constant here, and thus the limit of integration will vary from t naught to t. T is a variable since t corresponds to the time up to which we want to trace our particle, right? Thus t naught is fixed here in this case, and similar analysis could be explanation could be given for the y coordinate as well, where the limit of integration for y would vary from y0 to y, and time would vary from t0 to t, okay, where t0 is a constant now, okay. That's what we need to remember, right? So finally would get the equation of path line as these equations: ln x by x0 is equal to a p minus t naught plus t minus t naught whole square, and ln y by y0 is equal to b t minus t naught. And this equation is completely uh, uh, completely what to say, completely perfect as per se, because the equation now depends on x, y, and t, all the parameters that we can that can be easily plotted, and t naught and t naught, x naught, and y naught would be are known parameters, because we will know the initial time and the initial coordinates of the particle. So the plotting can be done for different instances of time to get the corresponding contour of the path lines, okay. Okay, then we now discuss about the I hope it was clear up till now, and obviously if you have any doubt, just you can just go back to the lecture by Professor Chakraborty, and if you have any doubt you can ask me as well, or put the doubt in the discussion forum, okay. So now we discuss about the acceleration of fluid flow, okay. So again, for the sake of saving time, I won't dive deep into how these expressions are obtained. I guess that can be understood by the lectures. I will just discuss the basic formula for acceleration for different components of acceleration in a fluid flow from the Eulerian perspective, and then try to deduce some conclusions from the expression, okay. I hope that's clear. So the x component of acceleration, I will discuss all the three, show you the differences so that you don't forget, okay. So for the x component, ax will be given by dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z, okay. Similarly, ay will be given by dou u by dou t plus u dou v by dou x plus v dou u by dou y plus w dou v by dou z, and by dou I mean the partial derivative, okay. Forgive me my what to say, language, but this is what we have followed in our studies, so I follow that for my sessions as well, okay. So different teachers or people who take the course may term the partial derivative differently, but for my case I term it as dou, okay. So finally az will be given by dou w by dou t plus u dou w by dou x plus v dou w by dou y plus w dou w by dou z. And in all this explanation, because in the beginning it may seem quite cumbersome and difficult to remember, but it's quite simple actually. So you can actually consider acceleration as an linear operator over I would not say linear, but a operator on the velocity component, okay. Why not linear? Because it's because if it is say u here, then this term itself becomes non-linear, right? That's why. So let's just consider the acceleration acceleration as an operator over the velocity component, right? Then this acceleration would this operator now can be termed as, can be written as this, okay. The acceleration operator can be written as dou by dou t plus u dou by dou x plus v dou by dou y and w dou by dou z. So this operator would remain fixed, okay, for all the components. So the only varying parameter for different acceleration would be the different velocity components. Like ax would be given by dou u by dou t, where u is the parameter here now, right? And the operator remains the same, dou by dou t here, u dou u by dou x here, v dou u by dou y, and w dou by dou z. Similarly, and see, it's operating on u, right? and thus this expression. Similarly for ay, the acceleration operator would operate on v. Okay, so you can see that dou by dou t is here same, u dou by dou x is same, this one, v dou by dou y is same like this here, and w dou by dou z is same here like this, and it's operating on v. Okay, similarly for the z component of velocity, again the operator remains the same, dou by dou t, that is here, u dou by dou x, that is here, right, v dou by dou y, that is written here, and w dou by dou z, that is written here. So see, the operator remains the same, and here it is operating on w. Okay, so I hope this way of explaining helps you to remember the expression, because in many questions you're just directly asked to find the acceleration component, and if you just mess up the formula, you will mess up your answer. Even though your concept is correct, but if your formula is wrong, your answer would be wrong, right? You will mess up the solution. So just so that you can at least not mess up the formula, I'm trying to make you understand or remember, or at least understand the pattern of how these expressions are written. Okay, the details of derivation or the fundamental concept of acceleration, how it is obtained, can be understood by revisiting the lectures, but that's not the purpose of today's session. But my purpose is to teach you or make you understand how to apply those concepts to solve problems, right? So, and in order to know that, you need to know the formulas as well, and thus I'm trying to make you understand how to remember these formulas, or how to find a particular pattern in all the formulas, so that we can remember the formula correctly and thus apply it to our problems. Okay, because in many problems, as I say, you just need to, you are given the velocity components, find the acceleration, that's all. A 2-mark question in GATE, a 2-mark question in a 4-mark question ESE, say, right? It may happen, and that's why remembering these formulas, at least in the case of fluid mechanics and this particular concept, the concept of acceleration or total derivative, so that's very important. Okay, so I hope it will help you to recollect the formula. I'm emphasizing it again and again because such kind of things I myself have gone through, right? So if you remember the formula, you can at least get the numerical values correct, or the expression of the acceleration correctly, right? Even though if the concept is not that strong, but if the formulas are that you know, are that you know, if the formulas you know properly, you can find the solution. Okay, again, as discussed by Professor Chakraborty, this acceleration can be divided into two major components. First is a local acceleration, and second is a convective acceleration. Again, I will not dive deep how these two components are different or how they behave differently. There's a very beautiful example taken by Professor Chakraborty in his session. I insist you that you go through that, but for the sake of saving time, I don't think I will repeat that. Okay, so the fundamental of the fundamentals behind this dissociation of two components of acceleration, that is the local acceleration and the convective acceleration, is that the motion of the particle through the domain also causes a change in the velocity of the particle. Okay, not only change, but even a change in the flow parameter. Okay, not only velocity, but any flow parameter. It can cause a change in any flow parameter. That basically, since we are visualizing or understanding the fluid flow from the Eulerian perspective, and since all the flow parameters are dependent on both time and space, so the motion of any fluid particle through the domain would itself cause a change in flow parameter, even if this motion is locally steady. Okay, I hope I'm able to make it clear, but still, okay, there's a very beautiful example. Okay, let me just give it, okay, so that I may not repent that I was not able to say it, but let me just say it. Okay, so for example, this example, I guess, is written in Sengel, a book by Sengel on fluid mechanics. So he explains this local and convective acceleration with this example. Okay, so consider that you are in a cave. Okay, you are in a very say you are in North Pole and you are in a cave. Okay, you're standing in a cave, and say for the first case you just stand at a particular point, okay, a particular location, okay, and because of the change in the time of the day, that at the early morning it will be cold, then when the sun is when the sun is okay, let me just not use North Pole again, that creates a confusion of the day and night. Let us just say you are in a particular, a very cold place, okay, a very cold place, need not to be North Pole, say you are in Russia, okay, then since in the early morning and you are standing at a particular location, okay, for the first case, now because of the change in the time, say day and night, so at early morning it will be cold, right? Then as the sun rises up, because of higher level of radiations, uh, I won't use that even, but just say that because of the higher intensity of the sun, the temperature would increase, right? Even if you're not moving anywhere, just the change in the position of the sun in the sky would result in the change in temperature, the local temperature, right? And again, as the sun sets, the temperature would go down. So here in this case, you're doing nothing but just staying at a particular position in the cave, and this movement of sun in the horizon has caused the change in temperature, even if you're going nowhere, right? But now consider a scenario, the second case, which is more interesting, that this cave that you're standing has actually different gradients of temperature. It may happen that moving a different location in the cave, different locations of the cave may have different temperature, right? Because of, say, it can be for because of many other parameters, say the depth of snow surrounding the cave, or the existence of, say, certain holes, or sorry, exits, or just say there's wind flow at particular points of the cave, it may happen, right? So different points of the cave may have different temperatures now. And now as you move, say for a particular instant of time, if you move to these different locations, or just assume that for a particular instant of time, say for morning 9 to 10 a.m., the temperature remains constant, ideally remains constant, okay. And if in that particular instant of time, even if the temperature is locally constant, if you move to move to different locations of the cave, you will experience a temperature change, even if the temperature locally has remained constant, right? So this change in the temperature because of a movement through the cave, which itself has different gradients of temperature, is known as the convective derivative, or convective change in the flow parameter, okay, because convection itself means a mass movement of particles, right? So thus this additional component comes into picture in the case of Eulerian approach, that how the movement of particle through the flow domain has resulted in the change in the flow parameter, and in this case the flow velocity, okay. And thus the two components, the local and the convective component, contribute differently in in the net acceleration of the fluid flow, okay. I hope I was able to make it clear. And then finally we discuss about fluid deformation. These are the final two topics, fluid deformation and a continuity equation, where again I will not dive deep, just go through the formulas and their what conclusion they give, okay. So in the case of deformation of fluid, because we are going to discuss it again, this deformation can be decomposed into two parts, it is the linear deformation and the angular deformation. So in the case of linear deformation, we denote it by epsilon dot. So the linear deformation or linear strain rate along the x direction will be given by E dot x, which will be equal to dou u by dou x, okay. Similarly, E dot epsilon dot y would be dou u by dou y, and epsilon dot z would be dou w by dou z, okay. And finally, the rate of volumetric strain, from if we just recollect from the concepts of solid mechanics or centrometer, how the volumetric strain is found by the sum of linear strain rates. So the volumetric strain rate is given by, similarly the volumetric strain rate would be given by the sum of all these linear strain rates along the x, y and z direction. So the volumetric strain rate would be dou v by dou x plus dou v by dou y plus dou w by dou z. Okay, which would be E epsilon dot x, epsilon x dot plus epsilon y dot plus epsilon z dot. Okay, which would directly just give us the divergence of the velocity field. Okay, so the rate of volumetric strain divided by the volume gives us the divergence of the velocity field. Okay, this is a very important definition. Okay, why? Because see, divergence of velocity field like obviously has a very in-depth meaning when we consider it in the mathematical point of view. Okay, but since this mathematical expression is trying to explain a physical phenomena that is of incompressibility, we need to be able to correlate this mathematical definition with a physical understanding or physical meaning to the particular phenomenon that we're going to try to explain, right? So we are saying that the 1 upon the volume of dou v by dou t multiplied by the inverse of the volume is the divergence of the velocity field, which comes from this expression, right, where we disregarded the higher order terms. Okay, then if the divergence of the velocity field is 0, right, we will consider both the we'll consider vice versa as well. So if the divergence of the velocity field is 0, it implies that the rate of volumetric strain of the particular fluid element is 0, right? Similarly, if we consider vice versa, that if we say in that way that if the volumetric strain rate of the fluid particle is 0, it would mean that the divergence of the velocity field is 0. Okay, so this is a very important definition or concept for understanding of the significance of what the divergence of the velocity field actually means. Okay, I believe that we discussed about what incompressible fluid and incompressible flow means, I guess, in the first or the second session itself. I insist that you go back to those sessions and see how you're now able to correlate these concepts. Okay, so finally we discuss the conservation of mass. So again, the derivation I'm not going to discuss. It's written here, you can just look in the screen, and I hope it's quite pretty self-explanatory because this was discussed by Professor Chakraborty. But the final equation that we get is that the conservation of mass is given by this equation. Okay, dou rho by dou t plus the divergence of this parameter, the mass flux. Okay, rho v. Okay, so once we and see, okay, not to get confused with, this is not the complete derivative operator. Okay, the complete derivative operator is given by dou by dou t plus v dot del. Okay, this is operator. Okay, not a equation or something. It is an operator, expression for the operator, and these two are not the same. Okay, you'll get to see how. Okay, oh, it is actually be written here. Okay, so this operator I think there's okay, yes, okay. So as you can see, this operator, this one, this is the uh, complete derivative operator. Okay, and this is not. Okay, so mass conservation, people may say that directly that this is the d rho by dt is mass conservation, but this is not. Okay, this just tells us that the density is constant. Okay, it does not mean that and that equation does not correspond to the mass conservation. Okay, so this was important. This equation corresponds to mass conservation, which is an additional term. The divergence of velocity field multiplied with the density of the flow. Okay, but it is just important that you don't confuse yourself that of this equation with this differential operator. Okay, just wanted to make it clear that if we now expand this equation, and this is a vector equation, right, which is valid for all coordinate system. Okay, so if we say that we are trying to write this equation for a Cartesian coordinate system, then it can be expanded in this form. Okay, and again we have a very important conclusion that a given velocity field must satisfy the continuity equation to define a possible flow field. Okay, so we can arbitrarily give any expression for u, v and w, right, but for that particular flow to physically exist, that flow must satisfy mass conservation, because see, mass conservation are one of fundamental laws upon which the entire physics of fluid flow or even solid mechanics is depends upon, right? These are universal laws, right? So in the case of fluid flow, as we'll eventually discuss, it is mass, momentum and energy conservation. These three laws are the fundamental laws that are being analyzed for any kind of fluid flow problem. Any given problem, if you are able to analyze this with these three statements of mass conservation, momentum conservation and energy conservation, you are good enough to be said that you have a fundamental understanding of fluid mechanics. Okay, and you're quite clear in your concepts and you're quite clear in your fundamental concepts. Okay, and this is how we are going to approach most of the problems that we're going to deal in the later part of the course, especially the mass and momentum conservation. Okay, that's why I want to make you feel I want to let you know that don't make yourself alienated with these kind of concepts, right? These are the integral part of analysis for fluid mechanics. Okay, then okay, so this is again a very special case that is being discussed by Professor Chakraborty. So okay, so for steady flow, since dou rho by dou t would be equal to 0, so for steady flow we would have nebula dot the mass flux would be 0. Okay, nebula basically this operator I'm saying as nebula. Okay, so for incompressible flow, again as I said, d rho by dt would be equal to 0. Okay, and where rho is a constant is a special case of incompressible flow. How? I will say here. Okay, so if we expand this equation, okay, if we expand this equation here from continuity equation, okay, see here also again we are missing continuity equation, not this linear operator. Okay, so from continuity equation, if we expand this, we get that dou rho by dou t plus u dou rho by dou x, or just expand this equation, v dou rho by dou y plus w dou rho by dou z would be equal to rho dou u by dou x plus rho dou v by dou y plus rho dou w by dou z. And for an incompressible flow, we know that nebula dot v is equal to 0, so these terms will go out, right? So we are left with dou rho by dou t plus u dou rho by dou x plus v dou rho by dou y plus w dou rho by dou z, and this term just physically corresponds to the complete derivative of the density. Okay, see again, as I was recalling previously, that dou by dou t u dou by dou x plus v dou by dou y and w dou by dou z is not something that is only inherent to evaluation of velocity only. See, it is also operated on density or any kind of flow parameter, say temperature as well. These terms, this operator actually is trying to express the convective part of, or the convective contribution of the flow that corresponds to the particular change in the flow parameter. Okay, so this is what it's trying to express, and this expression is not only not only related to only velocity, but can be considered for any flow parameter. Okay, it's just a linear operator, it's not linear, it's just a differential operator. Okay, not a universal law only used for evaluating the velocities. Okay, that's what I wanted to say. I hope I am clear, but again, these are fundamental concepts, so it just sticks to your mind once you go through it again and again and again. Okay, I'm just trying to reduce that period of reading. Okay, so that at least after 2-3 times you're able to grasp the concept. Okay, so from that we get that from this we can write that dou rho by dou t is equal to 0. Okay, because the divergence of velocity field is 0. Okay, so final statement was then the variable density flow can also be incompressible flow. How? Because see, this expression dou rho by dou t is equal to 0 tells that dou rho by dou t, sorry, d rho by dt is equal to 0 tells us that dou rho by dou t plus u dou rho by dou x plus v dou rho by dou y and w dou rho by dou z is equal to 0. And it might happen that even if this is not 0, okay, even if this is not 0, these terms can have values in a way that the net sum of this expression can be 0. Even if these terms are not individually 0, the value of the individual terms can be in such a manner that the net sum of all these expressions is 0, which will again correspond to that d rho by dt is equal to 0, but it does not mean that rho is equal to constant. Okay, but rho is equal to constant is a special case or a trivial solution to this expression. Okay, rho is equal to constant is a special or trivial case to this expression, but it does not necessarily mean that d rho by dt means that rho is equal to constant. Okay, it just means that the flow is incompressible. Okay, but does not say that rho is equal to density is equal to constant. Okay, it's a very important concept as well as a conclusion that we are going to get from today's session. Okay, and I hope that you recollect it again and again, because these kind of questions will be asked in very high level interviews, even at PhD interviews or faculty recruitment interviews. These kind of questions can be asked and is being asked in that in the interviews that I have faced. Okay, in my PhD interview as well, I have been asked this question. So I was fortunately clear at that time. I was clear about this, but I insist that you know about this thing so that it can help you in a very long run. Okay. Okay, then I hope it was clear. Then let's just now directly go to the questions. Okay. So again, these 3 questions are not that difficult. It's quite simple. Let us just go through it. Okay. So the first question is, okay. So the first question is, for a hypothetical flow, the velocity field from time t equal to 0 to t equal to 10 was u equal to 0, v equal to -3, and w is equal to 0. Okay, it is saying that for a time period of t equal to 0 to t equal to 10 seconds, the velocity field was given by u equal to 0, v equal to -3, and w is equal to 0. Then from the time t equal to 10 to 20 seconds, the velocity field was given by u is equal to 2 meter per second, v is equal to 0, and w is equal to 0. Okay, then you are asked to find the equation of streamline. Okay, for t is equal to 6 seconds and t equal to 10 seconds, 18 seconds. Okay, and I hope it's very simple again. So we just use the equation of streamline, the definition of equation of streamline here, right? So for t equal to 6 seconds, the velocity field would be within this time period, right? T equal to 0 or to t equal to 10 seconds, right? So we can just substitute the values of u and v in the equation of streamline. So here from that we get that v dx is equal to u dy. Then here, since v is equal to -3 for the time period between t equal to 0 to t equal to 10 seconds, we get that -3x is equal to constant, or x is equal to constant, which is the equation of the streamline. Okay, so from here we get that the correct answer would be x is equal to constant, right? Right. Similarly, For the second question, we do the same thing. We see that t is equal to 18 seconds comes between the time period of t equal to 10 to t equal to 20 seconds. So we need to consider this velocity field, right, rather than the first one. Similarly, just substitute the value of u and v in the equation of streamline to get that v dx is equal to u dy, then 0 dx is equal to 2 dy, integrate to get that 2y is equal to constant or y is equal to constant, right? So we get the solution to be C, right? Y is equal to constant. Let's go to the next question. Okay, these questions are again interesting. Okay, so determine the location of particle at t is equal to 5 seconds, which was located at point 10 at t equal to 0. Okay, so if you read the question, it essentially is asking us to find the equation of path line and then find the coordinate of the particle for a given time, which is say t equal to 5 seconds here. And it has also given us the initial coordinates of the particles, which essentially lets us to find the concept of integration that we'll get while integrating that linear differential equation, right? So for the for t equal to 5 seconds, the corresponding velocity field would be u equal to 0, v equal to -3 and w equal to 0, right? And the initial coordinates are also given here. So the equation of path line is given by this expression, right? We rearrange it to find the equation of path line as this, right? Since this term is 0, then x would be x naught. So the initial coordinate of the particle would itself be the coordinate of the particle after t equal to 5 seconds. Okay, at x coordinate. Okay. Similarly for y, we write that dy by dt is equal to v, then dy is equal to v dt. Then integrating, we get that y is equal to -3t plus y naught, right? Then just substitute the value of t and y naught here to get that y is equal to -5. So x and y after t is equal to 5 seconds for this particular velocity field would be 10 and -5. Okay, so our answer would be B, 10 and -5. Okay, see, if there's any mistakes in my calculation, you can just stop me in between and even rectify yourselves afterwards also. See, the concepts are important, not the final solution. Okay, final solution is also important, obviously, but at least for this particular session it is a concept that I emphasize much more. Okay, so concepts must be clear, solution it will come eventually, there's no much of an issue. Okay, so next part of the question is that I feel a bit more interesting and a bit more challenging. Okay, so next question is determine the location of particle at t is equal to 15 seconds, which is located at point 10 at t equal to 0. Okay, why this question is interesting? Because see, this path line is not independent of the initial position, right? So which would essentially mean that the particle will remember the previous velocity field as well, because even though the velocity field has changed after t equal to 10 seconds, say, but since the path line of the particle would remember the history of the particle, so our solution would also depend on the initial velocity field as well, which was from t equal to 0 to t equal to 10 seconds. So we also need to keep that in our consideration while finding the equation of path line. And this consideration is just taken as different, different regimes of integration or different sections of integration you need to do. We just need to break the integration into different parts. Okay, so if we go back here, so we can write it as that for the x coordinate. Okay, we write the velocity field as well. For the x coordinate, u varies from u is 0 for t less than 10 seconds and 2 meter per second for t greater than 10 seconds. Okay, so our integration would be now broken into two parts. Okay, so so basically the expression would be a partwise continuous, but okay, so again the limits of integration would vary from x naught to x. Okay, since it is path length, so the initial coordinates and it will depend on initial time of the initial instant of time.
initial position of the particle as well. Okay, so it will depend on t naught and x naught. Okay, for the x coordinate. And after integrating, we get that x minus x naught would be equal to 0. Since this is 0, it will go out. So it will be equal to 0 plus 2t minus 10. Okay, and since t is equal to 15, we substitute the value of t here and the value of x naught as well to get that x is equal to 20. Okay, this is the first coordinate. Then for y, you use a similar understanding that dy by dt is equal to v, where y is equal to 3 meter per second for t less than 10 and 0 for t greater than 10 seconds. Right? So again, just substituting the value of the limits of integration in this expression, because the integration has to be broken into two parts. That is first from 0 to 10 and then from 10 to 20, 10 to 20. No, 10 to 15, right? So once we do the integration, we get that y minus y naught will be equal to minus 310 minus t naught plus 0, because the next v equal to 0 for t greater than 10 seconds, right? So once we do that, just substitute the value of t naught here and y naught to get it y is equal to minus 20 to get our final answer as x and y is equal to 20 and minus 20, which will correspond to option B. Okay, I hope it was clear, and I really found this problem to be very interesting, because we need to consider the initial history of the particle as well. That corresponds to the initial velocity field. Okay, so it was quite interesting. I hope you now get to understand, even if it's just an analytical solution, but at least you get an idea of how the particle also depends on the initial, how the path length of the particle depends on its history, right? Its initial trajectory, its initial velocity field. Okay, so it was quite interesting. Okay, then for the next question, an infinitesimally small fluid element is subjected to velocity fields u is equal to kx plus y, v is equal to kx minus y, and w is equal to 0. So it is 2D velocity field. Okay, determine the acceleration of fluid element along x direction. We are just asked to find ax. It's quite simple. Just substitute just substitute the value of u and v in the expression of ax. If we go there, we get that ax is equal to dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. You can neglect this term because w is equal to 0. So dou u by dou t is again 0 because there's u and v both not depend on time, right? So we get that we just need to evaluate these terms. So we finally get that ax is equal to 2k square x. I'm not going to go to the details of the derivation, right? You can just see in the screen yourself. So from that we get that ax would be 2k square x. Okay, so option B. Okay, so next question is, which among the following statements is correct if k is less than 0? Okay, so the options are: the fluid element will not deform, the fluid element will elongate in both x and y direction, the fluid element will elongate along x direction and contract along y direction, and the fluid element will contract along x direction and elongate along y direction. So from the options itself, you are getting an idea that you need to find the linear strain rates along the different directions, x and y specifically, because the z component of velocity is 0, right? So we individually find the value of the linear strain rates along the x and y direction, which would be given by dou u by dou x, which is equal to k, and dou u by dou y is equal to minus k. Okay, which we got from these expressions. Okay, just take the partial derivative of u with respect to x and partial derivative of v with respect to y to get that dou u by dou x is equal to k and dou u by dou y is equal to minus k. And it is said that k is less than 0. So if k is less than 0, if k is less than 0, it will basically mean that this term will be negative and this will be positive, right? So it will basically mean that dou u by dou x would be negative and thus there will be a contraction along the x direction, and dou u by dou y would be positive since k is less than 0. So there will be an elongation along the y direction. Okay, Similarly, the third question is again, so the correct option would be option B. Okay. So the final question is, find the rate of volumetric strain of the fluid element in this flow field. Okay. So it's again very simple. So it will just be the sum of the linear strain rates along the x and y direction. So after we do that, we get that dou v by dou y, dou v by dou x plus dou v by dou y is equal to k plus minus k is equal to 0. So there is, the fluid element would not deform and the rate of volumetric strain is 0. Okay. So the correct answer would be option C. Okay. So let's just take the final question. I guess this is the final question. So the question is, the velocity components in a two-dimensional flow field are given as u is equal to ax minus by and v is equal to minus cx plus dy. Okay. And it is said that a, b, c and d are dimensional constants. Okay. Then find the relationship among coefficients a and d that is necessary for this to represent an incompressible flow field. Okay. So for an incompressible flow, we know that nebula dot v is equal to 0, or the divergence of the velocity field is 0. So just take the partial derivative of u and v. From that you would get that dou v by dou x plus dou v by dou y would be equal to a plus d equal to 0. And for the flow to remain incompressible, a plus d has to be 0, and that's why the correct answer would be option number A. Okay. Oh, okay. There's one more question. So which among the following statements is or are correct? Right. Let us, it's again conceptual question. You need to remember the definitions. But let us see. I have discussed it thoroughly. So I hope we are able to find the correct answers. Okay. A path line is a line which is the locus of temporary locations of all the fluid particles that have passed through a fixed point in the flow field. This is not correct because this is a definition of a streak line, right? So this is not correct. A streamline at any instant of time is an imaginary curve or line in the flow field so that the tangent to the curve at any point represents the direction of the instantaneous velocity field at that point. Okay, so this is correct. Option C is, a streak line at any instant of time is an imaginary curve the flow field so that the tangent to the curve at any point represents the direction of the instantaneous velocity at that point. So this is basically the definition of streamline. So this is not correct because it is not a streak line, right? And finally, option D is, streamlines, streak lines and path lines are identical for steady flow. I guess we discussed it and how this statement is very important and how it helps us in flow visualization. So this statement is correct. Okay. Okay, so I think that's all. So this is the last question now here. So the question is, in the Lagrangian description of the position, the position of a free particle in a given flow field is given by x is equal to x naught e to the minus kt and y is equal to y naught e to the power kt. Okay, and x naught and y naught are initial position of the free particle. At time t equal to 0, k is a non-dimensional constant. Then the given velocity flow field is steady and uniform, unsteady and uniform, unsteady and non-uniform, steady and non-uniform. Okay. So to do that, I guess we just need to take the derivative. We need to find the velocity field and try to see whether the velocity field depends on the time or not. Okay, depends on t or not. Okay, we just need to check that. So let us just find the velocity field from the given coordinates, expression of the coordinates. So we get that u is equal to dx by dt, which is equal to minus k x naught e to the minus kt. And here we see that x naught e to the minus kt is itself is equal to x. So u is equal to minus kx and v is equal to dy dt and k is equal to y naught e to the kt. But here again y naught e to the kt is equal to y itself. So v is equal to ky. And since here you can see that neither of these velocity fields depend on the temporal coordinates, so we can say that u and v are steady but non-uniform because u and v depend on time, because right, u and v depends on time. Sorry, I'm extremely sorry. U and v depend on the spatial coordinates, and that's why the flow is non-uniform. So the correct answer should be steady but non-uniform. Okay. So I hope that's all for today's session. That's all from my side. I hope that I was able to clear your concepts, uh, uh, and help you understand the concepts much help you understand the concepts in a better way by solving different kind of problems. So I hope it was helpful. So again, if you have any doubt, I insist you that you go back to the lectures of Professor Chakraborty. He has discussed ample amount of examples and numerical problems to help you to understand the concept, these core concepts that are going to build the base for the rest of the course. So I hope you're clear with these concepts. And again, thank you for attending today's session. Let's meet in the next week's session on Friday. Okay. Thank you. Then that's all from my side. Thank you.